Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And this is part 3 of an 8-part little mini-series on two-factor factorial design with interaction. And here we're going to look at partitioning the total sum of squares and then derive some of the scalar formulas for the expected values and the sum of squares. So as a reminder, the model is y equals mu times the one vector x alpha times alpha, x beta times beta, x alpha beta, alpha beta plus epsilon. Epsilon is normally distributed, mean vector 0, covariance matrix sigma squared I. And I would encourage you to go to parts 1 and 2 for more details on the model. Now, partitioning the sum of squares, the total sum of squares in matrix form is this. Y transpose I minus J Y, where J is the perpendicular projection matrix onto the column space of 1s. Now, if we add a well-chosen 0 here, so we add M and subtract M, and then multiply the Y's in, we get this. Now, we're done with the sum of squared error. It's always I minus M, where M is the perpendicular projection matrix onto the entire column space. That's a generalized inverse, but it's M. Now we take M and we develop the structure of M, this perpendicular projection matrix, in part 2. And that's what we do here. Now, let's look at it. So this minus J is right here. And then what's left over is the structure of M. Right? And I'm going to point you to part 2 for more details. Now the J and the minus J cancel. Then let's multiply these Y's in and we get this formula here. Well, that's the sum of squares for treatment A, sum of squares for treatment B. This is the sum of squares for the interaction, and then this is the sum of squared error. Now, to convert these matrix forms to scalar forms, that's what we do next. Now, the sum of squares for treatment A, we actually derived this in the previous little mini-series on two-factor factorial designs without interactions. And the same thing for treatment, sum of squares for treatment B. So here, the new piece, let's sum of squares for alpha beta, or the interaction term, was this that we just derived up here. Now, this matrix here is a perpendicular projection matrix, so it's idempotent, so we just multiply it by itself and we don't change a thing. But what this does, it allows us to transpose, sort of untranspose this and this. So we have a vector product of the same thing. And then when you multiply this y into each of those, you get these mean vectors. And the structure of these we also developed in part 2. But then this vector product translates to this. And I encourage you to go through that product to make sure that it does equal this, to make sure that it's right in your mind. Now the sum of squared error, we do something very similar. So this is the sum of squared error, and then M is actually it's perpendicular projection matrix on the whole column space. But since the interaction subspace is equivalent to the whole design matrix, we can just put in the M alpha beta, which is the perpendicular projection matrix, onto that interaction subspace. Then it's idempotent, we can multiply it, untranspose to the left, and we get this. Now when you multiply that in, we get this, and then this multiplied together, you get this triple sum. Expected values of these sum of squares is the expected value of the sum of squares for treatment A is, and then we plug in the quadratic form. And then I have a playlist called quadratic forms, and in there we derive the mean, the variance, covariance of these quadratic forms. And there it's the trace of that middle matrix times the variance plus the mean of y times that matrix mean of y. Then the variance of y is sigma squared I. So the sigma squared can come out front, and I times this, you just get this. And the trace of this is a minus 1. Here, the mean is x star beta star transpose. This is idempotent, so we multiply it times itself. And then, of course, this is also x star beta star, but we can sort of unfold or unpack that into this. And now we can untranspose that, and we have the same thing here transposed as we do here. But really the tricky part is this piece right here, or with this. So let's look at that. Oh, and maybe more detail there. So this is the perpendicular projection matrix onto the column space of alpha minus j. So it projects it into alpha, but orthogonal to the 1 vector. So this times that would be 0. This, you just get it back. This, since this is orthogonal to the x beta space, you can think of it like if you pre-multiply this by m beta, the perpendicular projection matrix onto x beta, you just get x beta back, so we haven't changed it. But m beta times j is j, m beta times m alpha is j, so it creates, it's 0. And then this is whatever it is. So that's how we go from here to here. Now, let's, so this piece here carries down. And here, if you multiply this out, remember this is just a matrix of ones and zeros. This becomes this right here. So it's the first component times a 1 vector of length bn, repeated all the way to xn. This vector times this matrix creates this vector. And now when we multiply these out, m times this, so like m times this, we're just going to get it back. And then m times this is going to, or actually we do j times that. We get the mean vector, right? This times that, and then j times this. But then this, which is this, that's just one piece of the vector. So now we have to multiply this times this, or this times this, and that's what this represents. And in scalar form, it's this. Excuse me. So very similar, we could do the sum of squares for treatment B, and we're going to get this. The expected value of the sum of squared error, the expected value of this quadratic form, and then it becomes, the trace of that matrix. But let's put in m alpha beta since they're the same. The variance plus this. But I minus m is the perpendicular projection matrix on the orthogonal complement space of x alpha. So this, it projects it to 0. So this whole thing is 0. And we're left with this. And that's why the mean squared error, so if you divide both sides by this constant, and then this becomes the mean squared error, that's why the mean sum of squares error divided by this constant is an unbiased estimate for sigma squared. Now, last page, sum of squares, the expected value of the sum of squares for the interaction. This is the quadratic form. Then this is the formula, right? The trace of this matrix times the variance plus the mean times that matrix times the mean. Then this piece here, so this is idempotent, which can be multiplied by itself, and then this half and this half treated separately. But let's look at this piece here and bring it down. Oh, so we multiply this out, right? This is here, and then this piece is here. But this, what's interesting is this is a perpendicular projection matrix onto the interaction space, but orthogonal to the column space of 1 alpha, x alpha beta, x beta. So this piece is 0. So it drops out, and we're only left with this interaction term, which is, you know, the one piece of this. So now when we multiply this times that is what we get here, but then we multiply that into each of those and we get this, right? The J creates a constant vector, and then this creates a mean vector, but in the structure of x beta, and so this is repeated a times. This creates, you know, a vector that's very similar, that, you know, projects it onto x alpha, so that's why it creates these little constant vectors of length bn. Oh, that should be bn. And then m beta projects it onto the x alpha beta space. And then this vector multiplied by, you know, times itself creates, you know, that's what this represents, creates this sum of, you know, formula in scalar form. Okay, well, that's all I have for this. I went kind of fast, but I encourage you to go through all these derivations and make sure that they're correct and you understand them. If you have questions, please ask in the comments. That's all I have for this video. Please like it and subscribe so you don't miss the next one. Thanks. Bye.